All right, guys. So this is the another slide that I've prepared for you. Again, this is exclusively and only for analysis how to use AWR and ASH methodologies and techniques to troubleshoot. Uh, okay, these are few questions that I've intentionally added to it. Like, I'm using the standard version. Can I generate the AWR and ASH reports? No, it's not possible because you have to purchase the Oracle tuning and diagnostic pack, and that requires separate license. If you want, I mean, instead of AWR, you can generate stats pack because that's now completely free. But if you want to make use of AWR and ASH reports, they are licensed feature. You have to purchase tuning and diagnostic pack. So another question is like, I am a developer and I do not have direct access to the server. Can I generate it by my own? Yes, using DBA tab, you will be able to generate the AWR report and ASH reports by your own, even if you are the developer. But again, that actually requires, you know, a couple of privileges added to your application account. For example, if you are not connected with the DBA account, then of course it's not possible unless you get some select any dictionary and few other permissions for AWR advisories. Until unless those privileges added to your application or custom schema, you won't be able to generate AWR and ADM even if you have the DBA tab added, right? And what are the use cases where these reports can be helpful? So when you have a problem, when your system is slow, uh, when you are seeing some really strange problems, and so it's basically give a clear picture of the database, what all is happening in the DB at the time when you have generated the AWR report, right? So next question is like any performance implication of these reports generating every 10 minutes or so? No, there is not any performance implication because there is this M1 light process that actually samples or collects data for AWR report per snap interval and per minute for the ASH. Right. Any difference that is between AWR and ASH that is generated on 10G and 12C and above? Well, the interface or the graphics or look and feel looks almost the same, but of course there is a though these two reports, AWR and ASH reports, are exactly the same, provides you some database metrics, but the ASH provides you more in-depth statistics of the wait events that is there on the SQL ID and session specific information, which somehow is missing in the case of AWR reports. Another thing is like, for example, you have faced a problem that happened on the database only for few fraction of seconds. For example, only for 15 seconds. So, and your AWR report, you cannot go below 10 minutes, right? So the minimum what you can generate an AWR report is 10 minutes, right? So, but what about the problem that happened on this busy system only for few seconds, only for 15, 20 seconds? So if you go and generate AWR report for 10 minutes, then there will be a big problem, right? So your stats will get averaged out, or you won't get that clear image of the state of the database at that during those 15 seconds, right? So it's good to generate the ASH reports because ASH reports give you the flexibility to generate the ASH report even for a 2-second period or a 1-second period. If you want to check what happened in the DB during that problematic 1 second or a 2-second, this is what you can achieve using ASH report. But that's somehow not possible in the case of AWR report. That's a huge difference in between the two. Okay. Any question?
No, sir.
Okay, now let's move to the next slide. So someone has, complained and dropped an email or maybe called you, and they said like some of the queries are intermittently or um, every now and then performing very slow, right? And then you checked the Oracle Enterprise Manager graph, the performance page. What you see is the concurrency weight class is very high. Let me enable the pointer first. Like for example, you have got around 98 CPU, right? And in fact, this concurrency specific weight has actually breached the maximum of CPUs as well. So the earlier instance, it's almost touched the maximum CPUs, but the another one is goes this peak, this mountain has actually hit close to 150. Um, right, so almost 150 average active sessions were found in the database waiting on the concurrency class wait event. right? And now customer also reported you like the performance get back to normal by itself, like they did nothing at the application, and in fact no DBA help they took, but uh, it actually comes and stays there for a few seconds or a few minutes and then automatically disappears, right? So that is really strange and bizarre problem. So they want to understand why it's that. So first, of course, you should go and generate the AWR report, right? Because AWR report here, if you go and check the system, because the best part with the AWR report is like it also provides you information about the OS statistics, right? Like how many CPUs are there, what is the version of your operating system, how many cores are there, how many sockets, the memory available. So this also gives you a clear picture of your entire system where you are actually doing the troubleshooting, right? Okay. But as I told you earlier, AWR, of course, is not at all a good choice for a shorter spikes. Like if your problem is there for 15, 20 seconds or only for a few seconds or few fraction of seconds, then of course, guys, it's not possible to get a clear picture of the system for those particular seconds of problem using AWR report. That is the problem, right? Okay. If you check this particular snip or snap that I've used, so this is basically from year 2011, right, from 1630 and 1700. So we have got a 30-minute snap interval, right? And if you do a divide of 5941.33 with 30.13, you basically get this figure called as almost 198. So around 200 active sessions which are basically waiting on something, right? What is that something? You are still not sure because you just opened the AWR report. You have no idea why so many sessions are there actively doing work and always waiting on concurrency event, right? But now using these two numbers, you get some idea, okay, system has really going through a lot of stress, a lot of work it has to do and process. And the figure is really very high, is more than double if you compare it with the CPU size, right? So uh, next thing, as I told you, and we discussed a few minutes back, like you should go and check the timed foreground events. So can someone please tell me now, because we just covered that part of top 5 and top 10 foreground wait events. So what is the biggest problem here? Where we should start from? Anyone?
Well,
So the
I'll
first one,
The first one probably which is causing 75% of the DB time,
Right,
71%.
right. Absolutely correct, friends. Absolutely right. This event, which is a latch cache buffer chains, or in sometime we performance consultants also called it as a CBC. CBC. So latch on CBC. This particular wait event, uh, this is actually with average wait time of 28 ms, right? 28 milliseconds, and has contributed 71.55% of the total DB time. Talking about the latch, as we discussed earlier, latch is basically very fast in nature, right? So it's not like a lock. Like for example, if you want, you can acquire a lock for days and weeks, right? So that will definitely cause some other problem. But yeah, if you have a latch that is waiting for even for this long, like 28 ms, because in the latching world, 28 ms is way too high because these latches are very fast, right? Because these are used by Oracle to prevent you multiple processes executing the same piece of code at the same time and to basically prevent some deadlocks, right? So uh, uh, I mean, you cannot subsequently acquire a latch at a level that is equal or to less than the level, right? So what I mean to say, for example, I am a session and I have an exclusive latch, right? So then another session comes and try to get its hand on that particular latch only. So the second session will go on wait, right? They will go and wait on any particular latch event. But if we talk about this particular event, latch cache buffer change basically protects the DB buffer cache architecture. So if we talk about the DB buffer cache, it basically contains some, some lists, some linked lists, basically, right? So a list-based architecture is there with the front and an end, right? So let me show you a figure I have for you for the CBC. This is the CBC or the cache buffer chain. So for example, you've got a parent latch, right? And you've got a child latch. So this parent latch called as cache buffer chain, right? And it has two separate latches, which is basically the child latches, right? And it prevents these three memory structure. Like for example, the latch one, this cache buffer chain latch one is responsible to protect chain one of blocks and chain two of blocks, right? Are you getting me?
No, sir.
No?
No.
Okay, where is the confusion?
Miss, this is the buffer which
Absolutely,
you are referring.
yes.
No?
Yeah, absolutely right. So let's assume notepad. Sorry, not notepad. Let me open paint. All right. Okay. So you've got an SGA, right? And within the SGA, you've got a DB buffer cache, right? Okay.
Right.
Right. So within the DB buffer cache, what is the purpose of having DB buffer cache, by the way? Why we have DB buffer cache?
It will put the block in the buffer cache, means whatever the read it from the
Absolutely.
disk.
Right.
Right.
So whatever processing, whatever modification that you actually do, you always need to do it in the DB buffer cache area. So it's basically this is what, we see the classical architecture, right? Of Oracle. Like you always have to keep a block. For example, if you have picked a block from the disk, you have kept it over here and do all of the modifications and everything. Once your modification is done, you do a commit, automatically DB writer will come and write this dirty block into the disk, right? And you will see the persistent image of the block, correct? But internally, what happens is this structure, this meshy structure is divided into like this. Like you've got 1, 2, 3, 4, 5, basically positions. So each of these blocks, which you actually keep here in the DB buffer cache, are basically maintained in the form of a list, an LRU list, least recently used list. Okay. So this list, this buffer cache location 1, 2, 3, 4, 5. So these are basically physical blocks which are kept over here, right? And then chain 2 is from 1 to 7. The length of these chains is different, right? The first chain has only got 5 elements, 5 blocks. The another chain 2 has got 7 blocks. Third chain has got 6 blocks, right? So imagine just, this entire mesh kind of a structure of a DB buffer cache internally, it's actually divided into these kind of LRU list or chains, right? So for example, if you have fetched a block from the disk through an IO and then you kept it in the chain 2, in the position 2 of this chain 2. Okay. Hello.
Yep.
Yeah.
So far you guys are good, right?
Yep.
Okay,
Right.
so you have placed that particular buffer or block into this chain 2 in DB buffer cache, right? But again, in order to scan and look out for a free space or a free buffer area in this list, you have to first and ask this parent and its CBC latch, can I go and can I get a exclusive latch so that I can go and traverse this list if there is any free buffer available or expired state block available or not, right? For example, it says the parent CBC buffer cache latch updates the session yes you can, I have free buffer, I have free latch, go for it. So first it will go to latch 1, it will check, okay, if there is any free buffer where I can go and keep my block for processing, right? So it will go and check chain 1, it start the traversal. Okay, when it reaches this location 1, it says, okay, this is busy, there is already one active block which is processed by some session. Then it reaches block 2, 3, 4, 5, no one is free here. It reaches chain 2, right? First is busy, second is busy, third, okay, yeah, this is free. In fact, the block which is kept here is now is in expired state, right? And the DB buffer will come anytime and will move it to the disk, right? So it will, reserve this space, this slot for him, for himself, for further process. So that's how, I mean, that's just an example, right? So in order to process, or in fact, let's assume you have a session that you're basically a second session, right? The session which executed just few minutes back executed the same SQL, right? And those required blocks are still present in the memory. So before Oracle Optimizer asks, or server process asks to read from the disk, because disk reads are always expensive, right? Memory reads are always faster, correct? So
Correct.
before they go and do the disk IO, it will always prefer and try to look if the blocks are 100% or partially available there in the buffer cache or not, right? So in order to do that check or that scan or the traversal of these chains, in order to look out for that particular block in question, they need to go and acquire the latch, right? And the latch that is for the buffer cache called as cache buffer chains, correct?
Okay. Yep.
Right? So now if you want to search for the required buffer or a block, you first need to ask if the latch is free or if I can get an exclusive lock so that I can go and traverse and travel around these lists in order to search the required block or a buffer. Correct? So that is the importance of the latches there in the memory, because they actually protect the structure, the shared structure in the memory. Correct?
Mm.
Any question or any doubt now?
No.
Okay. All right. So now when we know, like every now and then or very frequently, process need to search or scan the uh, the DB buffer cache area, right? So that means this request should be very, very fast. So that's what I said the term in the latching world. Latch weights of even 28 ms is a very, very huge amount of time. Usually that wait on latch happens only in, in millisecond, in microseconds and less than that, right? They're very, very fast. But if somehow this latch wait is in ms, or in fact, if it's in seconds, then you are in a big trouble, guys. Right? That means there is a very big problem simmering, right? And you have to immediately take care of it. Right? Okay. So that is why, because the Oracle has kept this wait event, latch, cache, buffer chains into concurrency class, because in order to maintain the shared memory structure concurrency, um, this wait, this latch needs to acquire. Correct? Same way. Yeah.
So what means we can suspect the reason behind this is because a particular table is heated so much or the number of transaction is very high.
Shubham, understand, this is just the very first slide that I've opened, right? So I have another 10 slides to go. Just bear with me for another few minutes, maybe 25, 30. You got answer for all of your questions by your own. Right? So this is just the start, right? You just generated the AWR from that problematic system. Now you just begin your analysis, because you cannot go and directly jump into the SQL, right? You first need to understand what is the weight and everything, right? Before you comment on anything. As I told you earlier, guys, again, the troubleshooting on databases is always comes with a great pain and a risk, because it always is actually full of getting false positives and false negatives. So if you feel like, okay, this latch free is the problem, or maybe this user IO direct path right is the primary problem, where you will be wrong, right? So you're actually passing wrong information to the team and for your own, right? And you're doing a wrong analysis of the system. Correct. So that is why be 110% sure, go slow, but yeah, strong. Okay. All right. So as I said, in the latching environment, in latching world, on latching universe, so waiting even for 28 ms is a very, very high amount of time. Right. Okay. I've actually intentionally copied one more snippet here. Like if you go and check this snap, it says NQTX row lock contention. So it's basically happens on the table, right? A transaction, a session is there, right, which is trying to modify something, but it haven't committed or rollback. The session is still active and then acquired a row in an exclusive mode. Now the second session comes and try to modify or manipulate the same row, then the second session will go in a wait state and it will start waiting on NQTX row lock contention, right? And why I purposely use this screenshot here, because if you take a look, the number of waits for NQTX roll lock contention is very, very low, right? But the average wait time is very high, 472 ms, and is it's basically responsible for 35.2% of the total call time or DB time, right? And is an application class or category wait event, right? So this is just an example. Let's focus here on this particular snap, what we have primarily used. So after seeing this, you can think, is this happening due to CPU? I mean, if we are CPU short, or if this is happening due to CPU starvation or what? So accordingly, you have to move ahead. Then next thing you have to check is the host CPU section. Like if you go and see the load average begin and load average end. Now, let me go back a bit. If you remember, like this snap is from 1630 to 17, right? So this is a 30-minute long AWR report. So right at the beginning of 1630, the average load average was 43. And at the end, I mean, at the end of those 30 minutes, 35.83 load was there. And out of it, around 40% load was there due to user sessions and system, which is hardly 3%. By the way, what is user percentage and system percentage from the load?
That is caused by the user IO and that is system IO.
System IO means what is system IO?
Caused with what are the means by the Oracle background process or
Not only by the Oracle background process. Remember, we are talking about the host CPU. We are not talking about the DB CPU here, right? So this is basically the system IO 3% means like out of the total uh, busy or the total load, only 3% was consumed in the system IO. System IO means when there are some recursive and internal operation that happens continuously by the operating system for internal scheduling mechanism, reading semaphores, right, doing some extent allocations for OS level blocks and so many other stuff that happens by through the operating system by its own, right? And that actually has nothing to do with the database or any software that you have installed on the operating system, right? For example, Oracle, but this is something by its own. Like for example, system himself actually used only 3% of the total. I mean, contributed only 3% of the total load, which was observed during those 30 minutes, right? And 57.7% was idle. So we have got a, a smart amount of a good number of idle CPU or the load available on the system. Like, I mean, plenty of idle CPU available here. So only for this 30 minutes of period, 30 minutes of AWR period. So more than 50% of the total CPU is idle. So I think that means that clearly answers the last question. Could it be CPU starvation or is this happening due to scheduling latency? No, this is not happening due to CPU. Otherwise, you would have seen a different figure here, something really less, maybe in few zeros or maybe 1 or 2, 3% as an idle percentage, right? So nothing is there from the CPU and CPU is absolutely fine. So we've got a lot of free and spare CPU cycles to be consumed by the processors, right? And one more thing, there is a problem with the load average in Linux, right? This load average in Linux also includes the disk IO, right? The time that you actually spends on reading or doing input output from the disk. So this figure basically on Linux operating system clubs that period too. And in complete or proper Unix systems like Solaris, AIX, and HPUX, this load always contributed to the CPU only the CPU. But nowadays, most of our installations happens on Linux, so we have to bear with this fact, and we have to understand like it's actually contributing not only CPU, but it also accounted for the disk IO that your process actually waits. Okay.
Yep.
Next is the operating system statistics. So again, the thing that we have finalized just in the last slide. So we have got ample of idle time available, a lot of CPU cycles or resources available in that context. So yeah, a lot of idle CPU cycles available. So yeah, this is not a CPU problem. Let's move ahead. Now, another section is the operating system statistics in detail. So for example, uh, though this AWR report was generated for 30 minutes, but the AWR interval on the database was for 15 minutes, right? So automatically your database will do the divide or will do the division, right? So you'll see from 1630 to 1645, this was the total system usage details, and from 1645 to 17 during those 15 minutes, this was the status. Now, if you take a look, last two columns are percentage of IO weight and percentage of IO. Don't you think like they are actually in the wrong column? I mean, percentage of IO, percentage idle should be 50.70 and 64.72, and IO weight should be 0.33 and 0.25. This is basically an AWR report bug, right? So that is why we are actually seeing a wrong information presented in a wrong column. So IO weight column should have 0.33 and 0.25, and idle percentage should be 50.70 and 64.72. This is a flawed metric, and that is why I sometimes do not rely on it, though they, both Oracle and RHEL has actually fixed this problem. But yeah, if you're running on an older version, especially on this Oracle database version less than 11G, so then you might face this problem within the AWR report where you're seeing some wrong information in the operating system statistics column, especially for this IO weight and idle weight. Okay. Now, next important thing, like let's first start with the SQL ordered by elapsed time, right? Okay, before that, let me ask you guys a question. Breathe a bit in between. Okay, guys. Yes. Can someone please tell me which is the SQL which actually took very high elapsed time?
The fourth one, 2.16.
Okay. Anyone else? Are you sure, Shubham?
Yeah, it has less execution and the execution elapsed time per second is
Anyone
high.
else? Shreya, I would like to listen from each one of you. Shreya, please.
We have to, I think we have to multiply. Yeah, total number of execution is also different. So per execution time, it's taking 2.16. So I
So
think
you're also saying 2.16 is the most expensive SQL in terms of the elapsed time. Manish, what is your take?
It is the number of execution will be the number of the higher count. Means if it is the elapsed time and we say the execution
I mean,
column,
from this
then
particular area of the AWR report, which one are you going to pick?
first,
Is
the
the
first
most expensive? First one?
Yeah.
Okay. Rest of you guys? Puneet?
I would also go with the first one.
You go with the first one. Saket?
Go.
You're also going with the first one, right? You're saying yes or no, Saket? Hello?
One. Yes, yes. First, going to the first one.
Okay. All right. So Puneet, Saket, and Manish saying first query is the most expensive, and Shubham and Shreya saying no. The one with the 2.16 is the most expensive. Actually, you guys are correct. 2.16, the query which is there with the elapsed time per execution of 2.16 second is the most expensive, right? Do not go with the overall elapsed time when you're checking the SQL ordered by elapsed time, right? Because if you go and take a look at the executions. Executions are way too high as compared to this one, right? Only 3,194 executions were noticed happening during that particular period of time, but with each execution it actually took 2.16. And if you check the elapsed time per execution in seconds column, none of the query is close to the average execution time of this query. Right, so that is why this query, and what is this query? This is doing some kind of an update. So this is the most expensive query, and you have to troubleshoot. You have to start your analysis if you are saying like they're expensive queries right on the basis of this elapsed time per execution column, not from elapsed time total seconds, because uh, this 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 section, this output is sorted on the basis of total elapsed time second. That's why it's always catches people eye, but actually the problem is not here. The problem, you should always go and check from elapsed time per second execution, like in single execution, single runtime details. Okay, let's go back. All right, now this was the screenshot I've captured for that problematic system, right? So as per this, the screenshot, which is basically a snip from SQL ordered by elapsed time, so that they are basically sorted on the basis of total elapsed time spent, right? If you go and check, elapsed time per executions of all of these SQLs are almost same, right? 16.36, 16.70, and this and that. And but what makes different the other queries is the total DB time. So you should start first with the with this particular SQL ID, like why it's taking 36.70% of the total DB time, though the average elapsed per execution in seconds is almost same with the rest of the queries, right? But this is something that actually makes different with the rest of the other SQLs, right? And if you go and check, this SQL is actually not CPU intensive also. Why? Out of the total 130,842 elapsed time for almost 8,000 execution, the total CPU time spent is only 19,643. I mean, that means this SQL is not CPU intensive at all. There is something else that is bothering this SQL. And is it really this SQL only? Can you really figure out? I mean, if that event latch cache buffer chain is happening all because of this query, it could be due to this, or it could be due to all of them, or it could be due to this, right? Am I right?
Yeah.
Yeah.
Correct. All right. So that is why it's important to keep doing your analysis. And next you have to check, because what this event says latch cache buffer change. So you have to draw an imaginary picture in your mind. When it says about latch, that means it's talking about something in the memory, in the SGA, right? And talking about the cache buffer chains, you need to understand it first. What is cache buffer chain or a CBC? Now you got an idea. That means something is there in the DB buffer cache. And what DB buffer cache is used for? For memory scans, right? For if we talk about the memory scans, then you have to go and jump directly into the SQL ordered by gets. Gets is basically used to represent the buffer gets or the memory scans. Whenever anything that that goes through the memory scans, right? So that means the problem latch cache buffer change, because that problem is related with the memory scans or with the DB buffer cache internal structure. That means something wrong is happening in the memory. And if you talk about the memory, that means if you want to check the sequels which are going for higher number of memory scans, that means you have to go and check SQL ordered by gets, that represents buffer gets. Right? There is another one called a SQL ordered by reads. That means disk reads. So for example, if you had got event called as DB file scattered read or maybe DB file sequential read, right? In that case, basically, you should go and try to look for, SQL ordered by uh, uh,
Hello.
by reads. Yes. Yeah.
Sorry, I just got disconnected for a while.
Okay. Are you able to hear me now?
Yeah, I'm able to hear you.
Okay. All right. So now you got the wait event. You have checked the OS statistics. Everything looks okay in terms of OS. You've got the event and you have checked the elapsed time as well. So there are multiple queries which are there with almost same elapse per second. But yeah, you are suspecting if this is responsible for latch cache buffer chain wait event or not. But again, you are only using AWR report. You have no idea, right? If that's the one who is responsible for it. But what else you can get from the AWR report is check the SQL ordered by gets, right? So what it says the total buffer gets is very high, right? For this particular SQL ID. This particular SQL ID 7G is the same one which is there and topping the charts for SQL ordered by elapsed time, right? But uh, almost same, right? With little different, we have got another one as well, right? So again, even after seeing that, I mean, you still do not have the clear picture. I mean, is this the SQL which is primarily responsible for latch cache buffer chain wait event, or there is something else, right? Let's check, because this is about the latch. So we have got a latch sleep breakdown within the AWR reports. So what latch sleep breakdown statistics provides you is basically the miss and the sleep ratio and the spin gets. So let me first of all explain you what exactly is that, right? So for latch, as I told you, latch basically uh, like for example, let me take the help of that screenshot, make things a little easy for you. Right. OK, this is the internal architecture, right? You have a session which is now want to scan a particular block from the memory, right? And you want to acquire a latch cache buffer chain. So for example, you go and because there is the number of latches are limited, right? If your database is very busy and your database goes through a lot of memory reads or DB buffer cache scans, then that means they might hit the time when the latches are insufficient or there is a shortage of latches, because there are already previous sessions who already acquired all of the available latches, and now your session comes, they are not free, right? So what they will do, it will count it as a miss because you are failed to get your hand on a latch the very first attempt, right? So what is the default behavior of latch is like it will go and do a spin. Basically, it wait for few quick fraction of CS centiseconds or maybe less than microseconds, basically, right? And then it again tries to get if the latch is free or not, or if their latch available, so that it can go and modify or scan this particular list, right? Again, it says no, is still busy, I do not have latch to provide you. It again goes for a spin, right? Then basically there is a limit called as spin gets, right? Or as which is controlled by spin underscore count parameter, right? And this parameter, if I'm remembering correctly, so this parameter is default to 2000. So that means almost 2000 time it actually tries on a very short period of time just to look out if if this latch is free, if I can get my hands on the latch so that I can process the block or I can traverse the list. So in that case, what will happen once that limit is crossed, then it will go for a sleep. It will go for some time to sleep, and that sleep is when the time when operating system help the process to be in a sleep state. So that is why it's important to check the latch sleep breakdown. So this statistic clearly says this latch called as cache buffer chains got these many requests, which is very, very high, and most of them are actually missed, right? And because it also goes to sleep state many of the times and also goes through the spin gates. That means, of course, there is a problem. I mean, sessions are not able to immediately get the latch. That is pretty much clear from this stat, right? Are you guys sleepy? No, it's only one man. I mean,
Your voice
No.
is breaking for me.
is it breaking for
Hello.
you only or for all of you guys?
No, it is
No,
coming.
not for me.
Okay, it's good for you. Okay, fine. All right. So this
Maybe
latch
I have
sleep
the issue.
breakdown. Yeah, so you can go and check latch sleep, latch statistics. This AWR report has latch activity, latch sleep breakdown, latch miss source, and mutex. So let's not discuss about mutex and pins here because that will actually make you more confused, right? So let's go. This is a different AWR report, by the way, but I'm just taking you to the latch sleep breakdown. It basically, that's how. I mean, there are different kind of latch. So in our particular case, like for this particular AWR report, problematic AWR report, where we see a lot of latch cache buffer chain events. So this, yes, this is clearly visible. It actually goes through a lot of get requests and a lot of misses happening and a lot of spin gets and a lot of sleeps happening. That means very less number of time people are, I mean, sessions are getting the required cache buffer chains in order to do the scan or traversal or checking of the scans in the DB buffer cache. But again, till this point, we do not know who and why does cause this contention, like what is the SQL ID and what is the SQL text, which actually caused this cache buffer chain. So let's move ahead. Next is the latch miss source, right? So basically this provides you information about the division of latch cache buffer chains, right? Because there are multiple, but if we talk about latches again, even the Oracle database itself is just a piece of a code, right? It's basically a big smart intelligent software which is again made up of thousand and million line of codes, right? So accordingly, within that particular code of Oracle, there is this latch definition mentioned again in a form of a code and in the kernel code basically. So this, if you check the latch miss sources, like what is that particular part of that latch which is frequently missed by the sessions. So it says KCBG Again, these are some short forms which are used by the Oracle software, right? Oracle code. So KCBG is nothing, it's just a representation of consistent read logical input IO function, right? And then KCB is for fast release. RLS stands for release, right? K stands for kernel. So this is just providing information like this cache buffer chain latch is if that's a full program or a code. In that particular code of a latch, this KCBG that's a fast path or CR pin, is basically going for maximum number of sleeps followed by fast release, right? So now you got little idea, like it's basically doing something for consistent reading, right? And that is why it struck. Next, now comes, the hero of this presentation, right? The hero is Ash, because so far you got no idea about the contributors, the SQL, the source SQL, right? Now, uh, again, I think I already discussed about Ash, like how exactly it generates the data, like how exactly it samples it and how it actually pushes into $V active session history and then move it after 60 minutes into active session, DB active session history. So let's not talk about it. So, but yeah, the important point is like Ash links, it helps you to bind, to link the relationship together, facts about the wait event and the SQL ID. So the relationship, like, okay, this is the SQL ID, and if this is waiting on this particular wait event, and that was the username, and that was the block, and etc. So that is something which is now provided by the Ash report. So now let's move ahead. Now, if you check, this is the section of the Ash report It says top SQL with top row sources. So it says this SQL ID with this particular SQL ID and this using this plan hash value and got sampled these many times. By the way, just for your information, guys, though the ASH basically samples every second of data into $$ active session history. That's basically the cached version of this view, but it actually pushes only 1 out of 10 snaps or samples from that $$ active session history cache view, only because just to save some space. Otherwise, if it actually keeps a track of the historical ASH samples, the table size will go tremendously and you will see the sysocs table space size is very huge. So just in order to save some time, it always prefer to push only one snap per 10 snaps or samples from the $$ active session history view to DB_active session history, right? Are you guys confused?
A little confused with the last thing. Means
What is that? Please help.
this ASH means we get to know the sample of executions here.
ASH is what? For example, you are doing your work, you're connected with the database and seconds is tickling, seconds is passing. So automatically the MON process is now actually collecting the statistics every second from the database for all of the sessions. Those are active and doing some work or waiting, right? And push that information and save that information into cache in a view called as $active _ session _ history. Let me help you. Okay, so this is the DBA $$ active session history, right? And there is this another view called as DB_hist_ active _ session history, which is exactly the same, but the only thing is like it actually helps to keep a historical information inside of it, right? That's it. Okay. Hello.
Yeah.
Okay, okay.
There you go. That is the historical version of the same view. DB_hist_ active session history, and the cache version which contain only an hour long data is the $$ active _ session history. Okay. Now coming back to the ASH. Do not get confused. ASH is the report. The ASH report gets its detail directly from these views. These views, DBA hist active session history and $$ active session history. That's it. If you are looking something from the history, then it always go and queries DBA hist active session history. If you're searching something which is fresh and still available in the cache, then probably go and look out something there in the $$ active session history. That's it. Okay.
Yeah.
All right. So now talking about the top SQL with the top row source, that is again a section in the ASH report. So it says 7G2H, this particular ID, which is using this particular plan hash value, got sampled 543 times 4 times and responsible for 40.85% of the total activity in the database during those 30 minutes. And yes, it's waiting on Latch cache buffer chains. And in fact, 20.83% of this particular row source, where it's actually applying some filter, right? So it's basically causing the problem. So yeah, but if you check rest of the 4 SQL, all of them are waiting on Latch cache buffer chains, right? So now you get an idea. This is not that single SQL which was causing problem or trouble to the database, but in fact, all of these 5 SQLs, all of them are actually waiting. Of course, this is the primary source. This is the leading contributor or primary contributor for this particular await event on cache buffer chains. But not only this one, we have got others as well. Correct?
Okay. Yeah.
So now I'm not going to discuss about the solution for the CBC because you have to devise your own plan, your strategy, look out for SQLs which are there in SQL ordered by reads and try to do some SQL tuning advisor, try to see if replacing an index, maybe a better index can prevent something, or you can also go and try to look if CPU is the problem. But fortunately, we are not facing the CPU starvation problem. But yeah, sometime I've seen like if the CPU starvation is the case, so you see some CBC specific weight events too, right? Okay, now let's move to the next one, next slide, which says, like if we talk about this latch cache buffer chain event, like this is about the 99.98% of the total activity. It says P1 value, P2 value, and P3 value. So you need to understand basically what is that. So let me help you with that. Where we are right now. Okay. These. Oh. Okay. Even in the AWR report, sometimes you see P1, P2, and P3 values. Are you familiar with these columns?
Yeah, this object ID,
Right?
P2 is object ID,
Absolutely
P1 is
right.
block.
Not always the object ID. It depends basically. Depend on the event. Like if we talk about the latch cache buffer chain, the P1, P2, and P3 value represent what? Latch cache buffer chains. Here is the latch cache buffer chains. It says the P1 value is the address. So that's basically this 16847241760 is the logical address, the memory address of that particular latch or that particular code basically, right? So this P1 parameter represents for cache buffer chains means this value, this particular number is pointing to the latch address, right? The next is P2 is the number, right? The latch number 144, correct? And the P3 is basically is why basically the reason sometime, but you usually receive 0 in case of the latch events. So yeah, the P1 and P2, if you really want to dig in deep the analysis, so what you can do, you can take help of P1, P2 parameters. Like P3 is the latch. Sorry, P1 is the latch address like this, and is P2 is the number. Like for example, we have got uh, other events too. Just a second. Let's try for DB file. Okay. Talking about the DB file scattered read, for example, what does the P1, P2, P3 parameter signifies? For DB file scattered read, it says the first parameter P1 is the file number. Next is the block number. And then it shows you the total number of blocks involved. That's it, right? So Shubham, I think I've answered your question, right? So it's not the same for all of them. So it depends on the wait events only. So for example, latch cache buffer chain, the P1 is the address, P2 is the number, and for DB file scattered read, the P1 is the file number, and then this P2 is the block number. Correct?
Yeah.
Okay.
So now if you check the top event P1, P2, P3 values, here if you see out of the total 99.98% activity, right, this is what it is. This is just a representation like what I just explained. Like the first P1 is the address, P2 is the number, and 0 is the tries. That's it. Move to the next section. So who exactly is blocking us, right? What is causing the problem then, right? So it says blocking SID was 5914 and serial 31561 instance 1. And but unfortunately, this is responsible for only 1% of the total activity. So out of the 100% activity, we only be able to understand or judge about this particular session only. No other records is present in the ASH report. So now we are really confused, right? Because we are not sure like who blocked us for 99% of the rest of the weights, right? For rest of the 99% cache buffer chain weight events, who all SIDs are responsible, correct? So let's move ahead. Now, if you go and check this next section, uh, here it basically shows more information. It says 99.98% is held in shared basically. What it says, it's ASH report incorrectly label unknown blocker, because here for 99.98% of this particular latch weight, the ASH report is not sure about the SID, right? So it usually it mention it as a held share, but it should ideally mention it as an unknown, right? So this is a problem, by the way. I think this is rectified now in the latest version of Oracle database. Otherwise, in previously till 11G release 1 or release 2 as well. So it's you always see held shared, but in fact this is representing like 99.98% of the total latch weight on this particular event is unknown. He's not sure about the blocking SIDs, correct? So only this SID 59143156, this one 59143156 is known to us, and that is really sad actually, right? But yeah, we'll devise a strategy like to discuss about it, right? Okay, next is the sampled weight. Sampled weight is out of the total weight events, how many weight event count is less than 10 ms. So out of the total weight on latch cache buffer chain, 161 samples are there with event weight of less than 10 ms, right? But yes, this is the blocker basically, because this the wait times that is between 10 ms to 100 ms, that's where maximum number of samples are waited on, right? But sometimes the weights are really too high, because take a look, like there are few events instances of waiting on latch cache buffer chain which is even beyond 1 second. And as I told you, in latch universe the weight of second is huge. I mean, it's humongous. It's extremely huge. It's extremely high, right? So you, of course, as we already saw, we are already in a very difficult situation. So again, I'm not leading you to a solution here, right? Because this is up to you how you develop your solution from this point. There are a lot of things what you can do, but again, you always, it's important to understand the wait event and prepare your strategy based around the event that is causing the problem, right? And then identify the SQL IDs and everything, right? Okay.
Okay.
I think, thank you very much, guys. So this is the end of this particular slide. Anything else you want to